Welcome to the lecture on the fifth law of ideal gas. And this fifth law is the Dalton's law. It's the Dalton's law. Okay. Now, at first, let us blankly read out what is Dalton's law. Let us at first blankly read out what is Dalton's law. So, according to the formal statement of Dalton's law, what we find, it's stated as at constant temperature, the pressure exerted by a mixture of two or more non-reacting gases, pressure exerted by a mixture of two or more non-reacting gases enclosed in a definite volume is equal to the sum of the individual pressures which each gas would exert if present alone in the same volume at the same temperature. So this is the formal statement. But at the first glance, you can't understand anything about this. You can't understand anything what Dalton is stating over here. It's difficult to visualize directly from the statement itself. So at the first glance, we don't understand anything. At the first glance, just we have gone through the statement blankly without understanding the statement deeply. Okay, so this is the statement of the law. But now what we need to know, we need to understand what exactly Dalton is stating, what exactly is happening over here. You have to understand the fundamental chemistry that Dalton is trying to interpret over here. Okay, so at first you don't give any try to understand this thing, what they're saying. Just we have seen that here we are dealing with a mixture of gases. It's a mixture of gases. This is very important. It's a mixture of gases, and these gases are ideal. Okay, and what you have maintained? You have maintained constant temperature. And you have maintained definite volume or constant volume. So you are dealing with a mixture of ideal gases. It's either a mixture of two gases or more gases, and the constraints are constant temperature and constant volume. And obviously, this mixture will comprise such gases which do not react with each other. So we are dealing with non-reacting gases. Okay. So we have kept temperature and volume to be constant. Okay, we have kept temperature and volume to be constant, and we are dealing with a mixture of two or more ideal gases which do not react with each other. And now what we are trying to do, we are trying to interpret something about the pressure. But that is not understandable directly from this statement. So we need to explore it more for the sake of deep understanding. Okay. So at first what we'll do, we'll move on to the next slide. We'll understand stuffs over there, and then again we will try to integrate that concept over here so that we can interpret this law completely. Okay. So this would be our modus operandi over here. Okay. So let's proceed into the next slide. So what we're doing, let's see over here. In this particular context, the thing which is very important is the term partial pressure. This term is very important, partial pressure. So before understanding the statement of Dalton's law, we need to interpret partial pressure at first. So this is the need of the hour. We need to interpret partial pressure at first, and then what we can do, we can interpret the statement that was given by Dalton. Okay. So what is partial pressure? For that purpose, at first, you have to understand two different situations. So in this slide, I will be depicting the first situation, the situation 1. The situation 1. What this situation is showing to you all? They're saying that you have taken all the gases together. You have considered an ensemble of gases, a collection of gases, and you have taken all the gases together. All the gases together. Where? In a flask. In a flask of fixed volume V. As I have already told you, I am going to maintain the constancy of volume. So we have taken all the gases in the ensemble together in a flask whose volume is going to be constant. And that is maintained at a temperature T. So again, the temperature T is also kept constant. So as I've already told you, the volume and temperature will remain constant. Okay, so they are constant, and you have taken a collection of ideal gases which are essentially non-reacting. Okay, in a flask, and due to the constancy of volume, you can say V is constant, and you have maintained constant temperature. Then it will exert the total pressure of P. That's saying that if you are keeping all the gases together in a particular flask of constant volume V, maintained at constant temperature T, then the total pressure is going to be capital P. Now we need to interpret this one. We need to interpret this one. And how we are denoting the gases? We are denoting all the non-reacting gases by a set J. Okay. And this set is comprised of a large number of gases. 1, 2, 3, 4, etc. And I is an arbitrary gas. I can be 1, I can be 2, I can be 3, etc. So J is the complete set of all the non-reacting gases. Those are taken together, and the number can be infinite. You can have a large number of gases. You can have a large number of gases. Okay? And any arbitrary gas is denoted as small I. And the number of moles are denoted as small n with the subscript. With the subscript which denotes a particular gas. Suppose for gas 1, the number of moles is N1. For gas 2, the number of moles is N2. For gas 3, the number of moles is N3. Any arbitrary gas I, the number of moles is Ni. And the entire set is denoted as Nj. So J is the set of gases. Nj is the set of number of moles of gases. Okay. So this is the situation. So what you have? You have a flask, a container, whose volume is V, and you are keeping a constant temperature T, and this container contains all the gases 1, 2, 3, I, etc. And the number of moles for gas 1 is N1, the number of moles of gas 2 is N2, of 3 is N3, of I is Ni, and so on. And the number of moles will not change. Since the gases are non-reacting, they do not react with each other. So what will happen? The number of moles will remain constant. The number of moles will remain constant. The number of moles of each gas will remain constant. Okay. So this is quite understandable. This situation is quite understandable. And they're saying that under this situation, the total pressure exerted by this ensemble is P. Now you wish to interpret this pressure. You need to find out a mathematical interpretation of capital P, which is supposed to be the total pressure. Okay. So for that purpose, we need to explore situation 2. So let's proceed into the next slide. चलो देखते हैं नेक्स्ट स्लाइड. A very interesting fact would be revealed over here. A very interesting fact would be revealed over here. We are yet not acquainted with the term partial pressure. I've introduced the term partial pressure, but I haven't defined what is partial pressure. I haven't interpreted what is partial pressure. But right now, in this particular slide, we will understand the meaning of partial pressure. And once we decode the concept of partial pressure, we can interpret Dalton's law. So, decoding of partial pressure is essential for the interpretation of Dalton's law. So, this is going to be very interesting to you all. Say, we're moving to situation 2. Now, what we are doing, we are taking the same flask that was taken in situation 1, whose volume was V. Even we are maintaining the same temperature, the temperature is constant. So, in this particular problem, volume and temperature doesn't cause any headache. Volume and temperature, they do not cause any headache. Why? Because all throughout they are affixed. All throughout they are affixed. We have kept them constant. Understood? Now, what's the difference between situation 1 and situation 2? In situation 1, we have taken all the non-reacting gases together in this particular flask. And the set was denoted as J. J is comprised of a huge number of gases, out of which I is an arbitrary gas. Now the difference is, in the previous situation, in situation 1, we have taken this entire set into this particular flask. But here we will just take I, whose number of moles is Ni. We have taken a single gas over here. A single gas over here. I can be 1, 2, 3, anything. We have taken a single gas over here into the flask. And the flask is same, with whose volume is V, and here also keeping the temperature constant. So only gas I is taken. It's kept in the same flask whose volume is V, and you have also kept the same temperature. So you can relate this concept with this diagram. You can relate this situation with this diagram. So you have understood this one? Now let's proceed a bit. Then they're saying, Under this situation, the pressure exerted is given by Pi. The pressure exerted is given by Pi. That's in the previous situation, in situation 1, you have kept V constant, T constant, you have kept all the gases together whose number of moles were N1, N2, N3, Ni, etc. In that situation, the total pressure was given by capital P. This was situation 1, and this is situation 2, where you have chosen any arbitrary gas out of this particular set. Say you have chosen gas I, you have kept gas I over here, but you have maintained same volume, you have maintained same temperature, and even the number of moles of gas I in the first situation is same as that in the second situation. But the difference would be reflected in the value of pressure. In the previous case, the total pressure was represented as capital P, and in this case, the pressure is represented as small p with a suffix I. Suffix I pertains to gas I. Okay. Then this pressure is said to be the partial pressure of I. Then this pressure is said to be the partial pressure of I. This pressure is said to be the partial pressure of I. This pressure is said to be the partial pressure of I. So this is the partial pressure. How does that come up? How does that come up? That means gas I in situation 1, gas I will contribute Pi towards the total pressure P. In situation 1, now you just think of situation 1. In situation 1, the total pressure is capital P. Then what would be the contribution of gas I towards the total pressure? The contribution of gas I towards the total pressure, would be P. Sorry, the contribution of gas I towards the total pressure P is Pi. The contribution of gas I towards the total pressure is Pi. That means in this situation where the total pressure is capital P, gas I is going to contribute its partial pressure Pi. What would gas 1 contribute? Gas 1 would contribute its partial pressure P1. What would gas 2 contribute? Gas 2 will contribute its partial pressure P2. What would gas 3 contribute? Gas 3 would contribute its partial pressure P3, and so on. So if you are keeping all the gases together under the constraints defined over here, you will see that the total pressure is going to be capital P. Now, this capital P is coming out of the contributions of pressures for different gases. So what would be the contribution of gas 1? The contribution of gas 1 is P1, or rather the partial pressure of 1. And what is the partial pressure of 1? Very simple. You replace gas I by gas 1. If you keep gas 1 over here, then its number of moles is N1. What would be the pressure? The partial pressure is going to be P1. So what you are doing? You are replacing I by 1, then Ni by N1, and then the partial pressure Pi would be replaced by P1. If you are keeping gas 2 over here, you are replacing I by 2, then the number of moles would be N2. and the contribution towards partial pressure, towards the total pressure would be P2. That means P2 would be the partial pressure. So now you forget about situation 2. Situation 2 is hypothetically constructed so as to understand situation 1. So let us forget everything about situation 2. Because we have understood the concept. We have understood the concept of partial pressure. Now we would solely focus on situation 1. So we have revealed the meaning of partial pressure. What is the meaning of partial pressure? Partial pressure is the pressure. It's the partial pressure of a particular gaseous component. Partial pressure of a particular gaseous component is what? Is defined as the individual pressure. It is defined as the individual pressure which a particular gas, say gas I, would exert when? If present alone, if it is present alone. Where? In the same volume at the same temperature. So this is the partial pressure. This is the partial pressure. This is defined as the partial pressure. Okay. So we have understood the meaning of partial pressure. Now let us solely focus on situation 1. Let us solely focus on situation 1. So in situation 1, what do you have? Again, let us draw it. In situation 1, we have a flask of constant volume V maintained at constant temperature T. It contains all the gases 1, 2, 3, etc. I. Number of moles of gas 1 is N1. Number of moles of gas 2 is N2. Number of moles of gas 3 is N3. Number of moles of gas I is Ni, and so on. Now what contribution would gas 1 make? Gas 1 would make a contribution of P1 towards the total pressure. What is the total pressure? The total pressure is thought to be capital P. So gas 1 would make the contribution of P1. What is P1? P1 is the partial pressure of gas 1. How would you get the partial pressure? Very simple. You take the same flask, you keep gas 1 only, you maintain same temperature, same volume. Same flask means same volume. Same number of moles. Same number of moles. Then the pressure you are getting is P1. P1 is the partial pressure of 1. So gas 1 is contributing P1 towards the total pressure P. Gas 2 is contributing P2 towards the total pressure P. Gas 3 is contributing P3 towards the total pressure P. Gas I is contributing Pi towards the total pressure P. So this total pressure arises out of all these pressures. This total pressure arises out of all these pressures. So this total pressure, you can write this total pressure P equal to the sum of the individual partial pressures, means P1 plus P2 plus P3 dot dot up to Pi plus dot dot etc. Very simple. Because this total pressure arises out of the partial pressures of each and every gas. That means you sum up all the partial pressures of all the gases present in the container, you will get the total pressure. So in simple notation, you will write it like it is equal to summation over Pi. So the total pressure is nothing but the sum of the partial pressures. Total pressure is nothing but the sum of the partial pressures. And partial pressure is the pressure that is exerted by a particular gas if it is kept alone in the same container of same volume maintained at same temperature, and you are taking the same number of moles as it was there in the mixture. Okay. That means you can understand this. If this gas 1 has pressure P1 represented by 2 apples, and gas 2 has pressure P2 represented by these 3 apples, then what would be the total pressure? The total pressure would be P1 plus P2, then it will contain 5 apples. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is the total pressure. Gas 1 plus gas 2. Understood? Understood? I think you all have understood this one. So now let us again move back. Let us again move back to the fundamental statement that was given by Dalton. Let us again move back to the fundamental statement that was given by Dalton. We have arrived at the fundamental statement of Dalton. See. Now let's read out the statement once more. Now we will understand the meaning of the statement. Okay. So at constant temperature, understood. The pressure exerted by a mixture of 2 or more non-reacting gases enclosed in a definite volume, understood. That means you are keeping the volume constant and you are measuring the pressure of a mixture of gases which are essentially non-reacting. It is equal to the sum of the individual pressures which a gas should exert if present alone. As I have told you, the total pressure is equal to the sum of the partial pressures. And what is partial pressure? Partial pressure is nothing but the individual pressure which a gas would exert if present alone. This entire thing is nothing but the partial pressure. Where? In the same volume at the same temperature. So what you have done? You have maintained constant temperature, you have maintained constant volume, you have maintained constant temperature, you have maintained constant volume. Now under this constancy, what you see? You see that the pressure exerted by a mixture of 2 or more ideal gases, you are taking a mixture which enclosed in a definite volume. Volume is fixed. What do you see? You see it is equal to the sum of the individual pressures which each gas would exert if present alone. That means it is the sum of the individual partial pressures. It is the sum of the individual partial pressures. It is the sum of the individual partial pressures. Understood? Okay. So this was the statement. At constant temperature and volume, the total pressure exerted by a mixture would be equal to the sum of the individual partial pressures. That's what Dalton is saying over here. So this is quite understandable. Now let's move back to the next slide. Okay. So let's move back to the point 5 where we were. So I've understood this one. I've understood situation 2. I've understood situation 2. Now we would like to make a mathematical interpretation of this thing. Very simple. You see, In situation 2, you have gas I, whose number of moles is Ni, volume is V, temperature is T. And it exerts a pressure equal to the partial pressure given by Pi. Then obviously, by ideal gas law, Pi multiplied by V should be equal to NiRT. Pressure multiplied by volume equal to number of moles multiplied by RT. That means Pi should be equal to NiRT by V. So this is our equation number 1. Understood? Now let's make further mathematical interpretations. So we have two equations now. We have got Pi equal to Ni RT by V. We have got total pressure P equal to summation over Pi. Now you substitute the value of Pi over here. So on substitution you are getting summation over I of Ni RT by V. In place of Pi, I am writing Ni RT by V. And we all know that T is constant, V is constant, and R is the universal constant. So RT by V is a constant. And this constant would definitely be pulled out of the summation series. So you are pulling out the constant of the summation series. The constant is being pulled out of the summation series. So if you pull out the constant, what you are getting? RT by V multiplied by summation over Ni. RT by V multiplied by summation over Ni. So you are getting total pressure P to be equal to RT by V multiplied by summation over Ni. And this is the partial pressure. Okay. So I think you all have understood this much. We have done a very simple mathematical interpretation and we have understood that Pi is equal to NiRT by V. P is equal to summation over Pi. Now you have substituted NiRT by V in place of Pi. And here Ni is the variable but RT by V is a constant. So you have pulled RT by V out of the summation series. So you are getting RT by V multiplied by summation over Ni. So total P is becoming RT by V multiplied by summation over Ni. Understood? Now let's move into the next slide. So what we have got till this much? Till this much we have found Pi equal to Ni RT by V. P equal to RT by V multiplied by summation over Ni. Now if you divide these two, what you are getting? Pi by P. If you divide these two, then Ni RT by V divided by RT by V multiplied by summation over Ni. You are getting this. You are dividing Pi by P. This RT by V will cancel out. So you are getting Pi by P to be equal to Ni by summation over Ni. Ni remains as it is. What is summation over Ni? Summation over Ni means N1 plus N2 plus N3 plus dot dot Ni plus dot dot etc. So getting this? And this is defined as this ratio. This ratio or this fraction is defined as xi. This ratio or this fraction is defined as xi. This ratio or this fraction is defined as xi. Number of moles of I divided by total number of moles. Number of moles of I divided by total number of moles is xi. What is x1? Number of moles of 1, that is n1 divided by total number of moles. What is x3? Number of moles of 3 divided by total number of moles. So in general, we'll define xi as number of moles of I, that is Ni, divided by total number of moles. Now you have to understand the meaning of xi. Xi is said to be the mole fraction of component I. Xi is said to be the mole fraction of component I. It is the mole fraction of component I. And how is it defined? It's a fraction. You are taking number of moles of I and you are dividing it by total number of moles. So it's the number of moles of I divided by total number of moles. It's the number of moles of I divided by total number of moles. So obviously it's a fraction and it must be less than 1. It must be less than 1 because Ni is the number of moles of I. It is in the numerator, and in the denominator you have total number of moles. So obviously the numerator is smaller than the denominator. That is quite obvious. So if the numerator is smaller than the denominator, then obviously the fraction is less than 1. And that fraction is known as mole fraction. It's the mole fraction of I. Xi is the mole fraction of I, which means the number of moles of I divided by total number of moles is defined as the ratio of the number of moles of the component. Here the component is I with respect to the total number of moles present in the system. Number of moles of that particular component, ratio of the number of moles of that particular component, ratio of the number of moles of that particular component. Mole fraction of a particular component is the ratio of the number of moles of that particular component to the total number of moles existing in the system. Okay. So can you say what should be the minimum value of xi? And what is the maximum value of xi? If I is absent, then Ni is 0. At first let us write xi. Xi equal to Ni by summation over Ni. Now if I is absent, Ni is 0. If Ni is 0, xi is 0. So this is the minimum value. If I is absent, then Ni is 0. If the numerator of a fraction is 0, then the entire fraction is 0. So this interprets the situation where I is absent. I absent. And what can be the maximum value? The maximum value of a fraction is 1. Now can we interpret it? Suppose the system contains only I. Suppose the system contains only I and no other moles is present or no other gases are present. If the system contains only I and there is no other gas, if the system contains only I and there is no other gas, then what would happen? Then obviously the number of moles of I should be equal to the total number of moles. Obviously in that situation number of moles of I should be equal to the total number of moles. In ideal case, if you have more than one substance, more than one gas, then obviously the number of moles of a particular component is ought to be lower than the total number of moles. That is quite obvious. But if you just have a single substance and no other substance, then the number of moles of that particular substance is ought to be equal to the total number of moles, because you don't have any other substance. So if you have gas I over there, then this one and this one are equal. If you have just I, so number of moles of I is equal to the total number of moles present in the system. Now if the numerator and denominator are same, then obviously they will cancel and the fraction will be reduced to unity. So this means only I. That means the minimum value of xi is 0 and the maximum value of xi is 1. That means xi varies from 0 to 1. Xi varies from 0 to 1. And you have already got xi equal to ni by summation over ni, which is again equal to partial pressure of I by total pressure. And this value will range from 0 to 1. This value will range from 0 to 1. So this is the final mathematical expression of Dalton's law. Okay. Now students, let's move on to the next slide. So these were the results I was saying. Xi equal to Ni by summation over Ni. This is again equal to Pi by total pressure. And Xi ranges from 0 to 1. So you have understood this one. Let's move on to the next slide. Now we'll do a few problems. Our first problem. We have an assertion. If hydrogen and chlorine enclosed separately in same vessel, in a vessel you have hydrogen and in a vessel you have chlorine. Okay. Hydrogen exerts a pressure of 100 millimeter and chlorine exerts a pressure of 200 millimeter given. 100 and 200 respectively. In the same vessel at the same temperature will exert a pressure of 300 millimeter. So these two vessels are same. They are enclosed separately in the same vessel. That means volume of the two vessels are same. Temperature is same temperature. So obviously this is the partial pressure of hydrogen and this is the partial pressure of chlorine. It is going as per our definition. Then their mixture in the same vessel will exert a pressure of 300 millimeter. If you are keeping the mixture hydrogen and chlorine, volume temperature remains fixed, then the total pressure should be the partial pressure of hydrogen plus partial pressure of chlorine. That means 100 plus 200 millimeter. That means 300 millimeter. So obviously the statement is true, the assertion is true. Now the reason is Dalton's law of partial pressure states that the total pressure is the sum of partial pressures. Exactly, that is the reason why the pressure of the mixture is becoming 300 mm. So both the assertion and reasons are true. And the reason is the correct explanation of the assertion. So the answer is A. So the answer is A. Very simple. Now let's move on to the next problem. Let's move on to the next problem. So what you have? You have a gaseous mixture which is prepared by taking equal number of moles of carbon monoxide and nitrogen. So you have a gaseous mixture where the number of moles of carbon monoxide is equal to number of moles of nitrogen, and say the value is N. So you have a container where you have kept carbon monoxide and nitrogen. These are the two gases. Number of moles of carbon monoxide is N, number of moles of nitrogen is also N. And the total pressure of the mixture was found to be 1 atmosphere. The total pressure is found to be 1 atmosphere. This is given. What is the partial pressure of nitrogen? You have to calculate the partial pressure of nitrogen. So according to the final expression of Dalton's law, we know that partial pressure of nitrogen divided by total pressure is equal to mole fraction of nitrogen. And again, this is equal to number of moles of nitrogen divided by total number of moles. Total number of moles means here you have two gases. So number of moles of carbon monoxide plus number of moles of nitrogen. Okay. Now, what is the value of P? P is 1 atmosphere. This is to be determined. What is the number of moles of N2? It's N. What is the number of moles of carbon monoxide? It's N. What is the number of moles of nitrogen? It's N once again. So, Pn2 by 1 atmosphere is equal to N by N plus N means 2N. N will cancel out. So it becomes 0.5. So what should be the value of Pn2? 0.5 multiplied by 1 atmosphere. That makes 0.5 atmosphere. 0.5 atmosphere. Answer is A. The value of Pn2 is 0.5 multiplied by 1 atmosphere means 0.5 atmosphere. So the answer is A. Understood? Okay. Let's move on to the next problem. Again, you have an interesting problem over here. See, you have equal masses of helium, oxygen, and sulfur dioxide. So you have three gases over here. You have three gases. You have three gases. In the container, you have three gases: helium, oxygen, sulfur dioxide. And they're saying that mass of helium, mass of oxygen, and mass of sulfur dioxide are all equal with respect to each other, and say the value is m. Okay, got it? So you have got equal masses, equal masses. You have to calculate the ratio of the partial pressure of these gases. You have to calculate the ratio of the partial pressures. That means you have to calculate P helium is to PO2 is to PSO2. You have to calculate this value. How to do that? Let us suppose the total pressure to be P. So we know that mole fraction of I is Pi by total pressure, which is Ni by summation over Ni. So when I is helium, what will happen? When I is helium, XHE is equal to partial pressure of He divided by total pressure equal to number of moles of He divided by number of moles of He plus number of moles of O2 plus number of moles of SO2. Okay. Now, the data is not given in terms of number of moles. It's given in terms of mass. So what to do? You see. Number of moles means mass of I divided by molar mass of I. And here also you have mass of I divided by molar mass of I. So you have to do one more step. Number of moles of helium is mass of helium, which is M, divided by molar mass of helium. Mass of helium divided by molar mass of helium plus mass of O2 divided by molar mass of O2 plus mass of sulfur dioxide divided by molar mass of sulfur dioxide. So eventually what you are getting? See, this M will cancel out. This M will cancel out. So what you are getting? You are getting 1 by molar mass of helium multiplied by 1 by molar mass of helium multiplied by 1 by molar mass of helium plus 1 by molar mass of oxygen plus 1 by molar mass of sulfur dioxide. So this is the form. Okay. Okay. So we can equate P helium by P with this. So we can write P helium by P to be equal to 1 by molar mass of helium multiplied by 1 by molar mass of helium plus 1 by molar mass of oxygen plus 1 by molar mass of sulfur dioxide. Similarly, PO2 by P should be equal to 1 by molar mass of O2, just replace this by O2. This thing will remain the same. 1 by 1 by molar mass of helium plus 1 by 1 by molar mass of oxygen plus 1 by 1 by molar mass of sulfur dioxide. Okay. And PSO2 by P should be equal to 1 by molar mass of sulfur dioxide multiplied by 1 by 1 by molar mass of helium plus 1 by molar mass of oxygen plus 1 by molar mass of sulfur dioxide. So if you take the ratio of the left hand side, if you take the ratio of the left hand side, then this denominator P will cancel out and you are getting P helium is to PO2 is to PSO2, which is equal to, you are taking the, now you are taking the ratio of the right hand side, and when you are taking the ratio of the right hand side, this common factor over here, over here, over here will cancel out. You are left with 1 by molar mass of helium is to 1 by molar mass of oxygen is to 1 by molar mass of sulfur dioxide. And this is asked to be found out, ratio of the partial pressures of helium, oxygen, sulfur dioxide. What is 1 by molar mass of helium? Molar mass of helium is 4. What is the molar mass of oxygen? It's 32. And what is the molar mass of sulfur dioxide? 64. Okay. Now you multiply all the terms by 64, it becomes 16, it becomes 2, it becomes 1. Okay. Okay. The answer should be option C. Answer should be option C. There is a mistake in option C. This is 16 is to 2 is to 1. It should be 16 is to 2 is to 1. 16 is to 2 is to 1. So there was a mistake over there. A printing mistake. It should be 16 is to 2 is to 1. Okay. Understood? Okay. So this is the end of our lecture. Thank you all. See you in the next lecture.